In this video, we're going to take a look at FBDs. And FBDs are arguably the most important skill that you have to learn this year. It's at the very least one of the most important skills to learn. On the surface, it's going to seem like FBDs, once you get the hang of it, are really simple and what's the big deal? But FBDs guide everything that you do when it comes to setting up problems of all types. That includes not only force problems, but work and energy problems, as well as impulse and momentum problems, because those two concepts also include forces. So it's really important that you understand how to do these and that you do them accurately. So make sure that you're putting the time in to practice doing these types of problems, or just to drawing these diagrams. Now, an FBD stands for a free body diagram. And that's a mouthful, so we always just say FBDs in class. Now, free body is the important part of this equation. What does it mean to be a free body? Well, a free body is whenever you take the object of focus out of its environment. And your job is to focus only on what that object is experiencing. And that is easier said than done at times, but that's basically what we're doing with a free body diagram. And we're going to get a lot of practice at this year, so if you don't quite have the hang of it yet, that's okay. You know, we're learning, and it's just part of the process. Nobody's perfect from the start, and I wasn't either. If there is any trick to successfully drawing free body diagrams, it is this. And I would have to say this is really the key. Outside of knowing that force catalog. Remember, if you don't know the force catalog, then there's no way you could possibly do your physics accurately with any regularity. You're going to be messing stuff up all the time. But outside of that, if there is a key to accurately drawing free body diagrams, it is knowing this, that all forces are contact forces except gravity. All right. Now, I know I mentioned that before, but it's going to be very meaningful for us in this video. To put this in other terms, what we're saying is this. If it doesn't touch the object, then the force doesn't exist. Now, let me give you an example of that. Oftentimes, students will be presented with a question where a baseball or something like that is thrown. A ball of some sort is going to be thrown. And once the ball has left the person's hand, you're asked with drawing a free body diagram. Now, the person's hand is down here, and I know this looks a lot like cauliflower or something like that, but here's the person's hand. Here's the ball. The ball is moving in a path that's going to look like that. Is the ball touching anything? No. We're going to ignore drag, or we're going to ignore air resistance. That's something that we established all the way back in kinematics during your summer assignment in Unit 1. And so the ball isn't touching anything. So knowing that all forces are contact forces except gravity, if it doesn't touch the object, then the force doesn't exist. What's that mean? In terms of our free body diagram, we have one force which is acting on the ball, and that is the force of gravity straight down. But oftentimes, and this is the mistake, and I'm going to do this in, I'll do it in blue so that you know this is the common mistake. Students will mistake the force of the hand for still being on the ball, because what's making the ball go forward, right? That's the mistake that's always made. What's making the ball go forward? And the answer to that question goes back to Newton's laws of motion. It's inertia which is causing the ball to continue to move forward. All right, so the force of the hand cannot exist because the only non-contact force is gravity. And so the hand isn't touching the ball, therefore the ball does not have the force of the hand. So this does not exist. We only have this one force, and that's the force of gravity pointing straight down. So that's the idea behind this statement right here, developing that. If you can really truly wrap your head around this and never screw that part up, you are well on your way to being successful with drawing free body diagrams. Now, when we draw free body diagrams, there are various, I'll say, styles of drawing them. And I certainly have my own particular style that I suggest, and I'll explain why. Sometimes when you're drawing a free body diagram and you're reading somebody else's stuff, it might even be in your textbook, okay? They'll draw a dot, and the arrows will always come from the dot. And so the arrow might be the normal force pointing up, it might be the friction force pointing to the left, or something like that. Okay, but I am going to suggest that instead of drawing a dot, that you use a box. And the reason for that is that sometimes you have multiple forces which are pointing in the same direction, and it becomes very difficult to put all those forces pointing properly so that you have a nice drawing. Sometimes it's difficult to do that when all you have is a dot. So in my class, we generally are going to use boxes to diagram forces. And maybe that's because you've got the normal force pointing up, and then you've got a tension force which points in that direction. Then there's a friction force here, another force pointing down. But the point is, it gives you room to work. Okay, so when it comes to drawing FBDs, the first thing you're going to do is draw a box. And that box is going to represent the object of focus. Okay, and we're going to do some examples, so don't panic here. The second thing you're going to do is whenever you're diagramming your forces, you place the tail of the arrow, and the arrow represents our force vector. You place the tail of the arrow on the box. And the one thing that you always want to make sure you include is an arrowhead. Oftentimes students will omit the arrowhead, and when you do that, you don't actually have a vector drawn, and you don't know which way the vector points, because occasionally you will see a problem, and it could even be coming from a textbook, where the arrow is pointing like that. Now, it would be best to put it on the diagram like that. That makes more sense, but sometimes it's drawn like that. And so if you don't have that arrowhead, then things become a lot more confusing. In other words, if all you saw was this, is it pointing this way or is it pointing that way? Okay, all right, so include an arrowhead always. And that's it. Those are the two things that you have to do. You draw a box and you place the tail of the arrow on the box. The rest of it is dependent upon what forces are actually existing. So let's take a look at a simple example. Okay, in this example, what we have is a physics book which is just at rest on a tabletop. And we want to draw an FBD for this situation. We don't have to know anything else. All we know is that it's at rest on a tabletop. So the first thing we're going to do is we're going to pull the object out of the system, out of the picture. And there's my box, which represents the book. Then I ask myself, what's touching the book? Okay, so here's our first question. What's touching? And the answer, tabletop. That's all we have touching. So then we can ask the question, how many contact forces can exist? Not do exist, but can exist. And this is to help you get focused on the various properties of the forces in our force catalog. And right now, because we have one touch, that means two forces can exist. What are those forces? That's going to be the friction force and the normal force. Those are the two that may exist. All right, now, how many forces actually do exist? And the answer to that is going to be 1. Now, how do we know that there's only one force that exists? Well, let's go through this a little bit. If you go back to our force catalog, you're going to see that we're not in a fluid, so there's no buoyant force. Then you're going to see that there's no strings involved, so there can't be a tension force. There's no kind of random pushing involved, so we don't even have a generic force. It's not moving, therefore we can have no drag forces, which leaves us with the first two on the list. And those are going to be the two that you use most often anyways. And that's going to be the friction force and the normal force. Now, the normal force we know must exist anytime there's a touch. That's going to be the normal force. And so the normal force is going to point straight up. The friction force, it only exists if there's another horizontal pushing force of some sort. Either it's in motion and it's sliding, which it's not in this case, or if it's at rest, something else is pushing on the book. So if there was a person pushing to the right on that book, and the book wasn't sliding, there would still be a friction force that points to the left. But nobody's pushing on the book, nothing is pushing on the book, therefore there is no friction force. And so of the contact forces, we only have one, which is the normal force of the tabletop. Then all other forces are non-contact forces. The only other force that can exist is the force of gravity. And the force of gravity always points straight down towards the center of the earth. Always. Our FBD is now complete. There's nothing more that we can do to this FBD. And that's just how you go through each one of the problems. You just look at each of the forces in your force catalog, and then you decide whether or not the force exists based on the properties of the various forces. So let's go ahead and take a look at one more, and this will be example 2. And what we have here in example 2 is we have a desktop, we have a physics book on that desktop, and then on top of the physics book, maybe we have a dictionary. All right, so we want to draw an FBD for this particular scenario. And what I'm going to have you do is pause the video here and draw a picture very quickly yourself. Draw an FBD. Just see what you do with it. There's no harm in being wrong at this point. It's just to help get you engaged in this video a little bit more and maybe test the waters. Some of you, after seeing the first example, might be like, yeah, I'm ready for this. And others, you might not quite be ready. So go ahead and give it your best shot. Okay, so the first thing we're going to do is draw our box to represent the physics book. And we want to know, what does the FBD on this physics book look like? So the first question we're going to ask ourselves is, what's touching the book? Okay, so what's touching? We have the table, and then we have the dictionary. Then I'm going to ask, how many forces can exist? And when I say how many forces, I mean all the forces. All the forces that can exist. So what we know is this. We have two contact forces, or I'm sorry, we have two touches. And each of those two touches has the possibility of creating a second force, or up to two forces. So there's 4. And then there's only one other non-contact force that can exist, and that's going to be gravity. So how many forces can exist in this situation? We have 5 forces can exist. Okay, now, before we get to gravity, let's just take a look at the other two forces that are, or the other forces that are acting on the box. We're going to ignore the stuff related to fluids, and we're going to ignore the stuff related to strings, the tension force, and we're just going to take a look at the normal force and friction force. Okay. And what we have here is a touch due to the tabletop. Now, which way is the force due to the table acting on the physics book? The force due to the table is going to be pointing upwards, and we're going to call that the normal force. And that would be the normal force of the table. Now the dictionary is also touching, and the dictionary is pushing which way on the physics book? The dictionary is pushing down. So the dictionary pushes in that direction. So that's the force of the dictionary. Now, technically, that is a normal force. But notice I called it the force of the dictionary. And why would I do that? Because I don't want to confuse all these different normal forces. So it makes complete sense, and it's completely okay to say it's the force of the dictionary pushing down. Now, we have the two contact forces that always exist. Let's address the issue of whether or not the friction forces exist. And we go back to our first example as a model, and we can see that no. And the reason we can't see is what? Why don't we see the friction forces in this problem? If you said because there were no other forces that were horizontal attempting to push either the dictionary or the physics book, you would be correct. And so we don't have any friction in this problem. All we have are the two normal forces from the two surfaces. We've got the dictionary pushing down on the book, and we've got the table pushing up on the book. There's only one other force that can exist, which is a non-contact force, and that's the force of gravity. It's going to be pointing straight down, and it's going to look something like that. That's it. Our free body diagram is done. Let me bring up something as it relates to free body diagrams. We've done head-to-tail diagrams in the past, and we're going to be doing a lot of them throughout the year. We have two situations when we talk about forces. We have equilibrium, and then we have non-equilibrium. Now, equilibrium means that there is no acceleration. That does not mean that there's no motion. It just means that there's no changes in speed or direction. And then non-equilibrium, of course, implies that you have acceleration. Now, when we look at these books sitting on the tabletop, we know that there's no acceleration because they're at rest. They're not changing direction, they're not in motion in any way, and therefore they're in equilibrium. So the total force which is acting on the books should be 0. So when we draw our FBDs, the arrows should be approximately the correct size. Approximately. And that allows us to draw a head-to-tail diagram so that we can confirm that we've included everything that we should. Okay, so this is equilibrium. Head to tail, we're going to have the normal force of the table pushing up. Then we get the force of the dictionary pointing down. And then we have the force of gravity pointing down. And notice that we're at the same level right here, which is where we started. And so basically, we're in equilibrium. So in this video, you should have learned the basic process of drawing free body diagrams. The free body diagram starts off with a box, and if you want to, you can do a dot, and you draw arrows which represent your forces. The tail of the arrow should always go on your box or on your dot, and the arrow should always point in the direction with an arrowhead that the force is actually pointing. In order to identify the forces that are acting on the object, you ask yourself, what's touching the object? If you've only got one thing touching the object, that thing can only provide up to 2 possible forces. And there are some things, like strings, for example, which can only supply 1 force. All other forces, therefore, have to be non-contact forces, and we only have one non-contact force, and that's gravity. And gravity is always going to be pointing in one direction, that is down relative to the surface of the earth or towards the center of the earth.